Today we'll be talking about vector machines, logistic regression, neural nets, and some other evaluation metrics that you may not have seen before. Just a few announcements. When we're going to do half an hour ago. Although if you do need to take late hours, that is fine. You could see it later today or tomorrow. Homework 2 has been released. It'll be due next week, Tuesday at 2 p.m. by Moodle. So just to recap. So this is the story that we've been following so far in the class, where we have training data, choose a model class, we've been looking only at linear models, data lives in some d-dimensional space of features that maybe we handcrafted or just raw features. We have labels that are binary, we choose the loss functions and the square laws, and we solve an optimization problem. And this is the recipe that is conventional machine learning that most people have found useful in practice. We've talked about bias variance trade-off, which is one way to think about how your model is overfitting. If you don't have enough training data, even if your model class can fit the data very well, if your training data is very few in number, then you could have high variability depending on the randomness of the training that you create, which leads to high variance. So choosing a model that optimizes the bias variance trade-off is one that leads to best performance in practice. And this is the entire pipeline, so the additional step here is that you want to do some sort of validation and model selection in order to make sure that you are tuning your model complexity in a way that it generalizes well. And we also talked about last lecture how to solve this using stochastic gradient descent for squared loss. Today, we'll be talking beyond just basic linear models that minimize squared loss, or perceptron. We'll be talking about a range of models. Most of them are still linear models, but they minimize loss functions that are not squared loss. So support vector machines, logistic regression, we'll talk about neural networks and different ways to interpret these models from a geometric or algebraic point of view. And then I'll end this lecture with a little bit of discussion of different evaluation metrics beyond 0-1 loss and squared loss. Okay, so recall that when we want to solve our optimization problem, the loss function, at least for binary classification, the loss function that we really care about is 0-1 loss, right? If your model makes the correct prediction, or the sign of the scoring function is in the correct sign, then we have 0 loss. If the sign of the prediction is in the incorrect sign, we have 1 loss. That's the loss function that we really care about because it is directly equivalent to accuracy, right? Expected 0-1 loss on your training set is equivalent to accuracy on your training set. Right? Of course, 0-1 loss is either flat or discontinuous everywhere. So doing gradient descent, which is what we talked about in the previous lecture, is really not possible, right? The gradient here is 0. You don't know if you're supposed to go this way or this way, and the gradient is similar over here, and it's completely discontinuous. So what people typically do is optimize some surrogate loss function. One that we talked about already is squared loss, which we use for regression, but we can also use for classification as well, right? Regression, squared loss is a differentiable loss function, and it gives, and as you take the derivative, you'll eventually get to the optimal solution, especially in the case where there's just one variable. So just to recap, 0-1 loss is what's known as intractable in the optimization literature. It's flat or discontinuous everywhere, very difficult to optimize. And the goal instead is to optimize some surrogate loss function that is related to 0-1 loss, but easier to optimize. And today, we'll start with the hinge loss, eventually. And the hinge loss is what's optimized by support vector machines, also known as max margin classifiers. So we talked a little bit about in the discussion about perceptrons, right? Where we want to converge to a model that splits the data, right? And so here's 3 different models that split the data in different varying degrees of accuracy. The first 2 obviously is not that good, and the third one is somehow the best one, right? And in some sense, it's of all the classifiers that separate the training data, this model, H3, is the one that somehow splits the model the best. And we can measure this through a notion of margin. And what the notion of margin, as we talked about in the previous lecture, is basically the distance between this line, which represents our separating hyperplane, our model, from the training examples, right? We could choose another line, like H2, which also completely has 100% accuracy on the training examples. But the margin is much smaller, right? The distance between the positive and the closest positive and negative points to this line is much smaller than this one. So in some sort of geometric sense, H3 is a more reliable or a more consistent or resilient classifier than H2, right? You can imagine if I just like got another sample of training data and the points would just jiggle around a little bit, the H2 may no longer have 100% accuracy in the training set. But if I drew another sample from the training set and the data points would jiggle around a little bit, I have very high confidence that H3 will still get 100% accuracy on the training set. At least ones of this size. And so that's the intuition behind support vector machines. So just a little reminder about hyperplane distance. A model W, a linear model is parameterized by a multidimensional W and a scalar B offset. And you can think of it as the norm of some hyperplane that splits the data, and the signed distance between any point x and this hyperplane is denoted by this formula, which is simply the scoring function of our linear model divided by the norm of the weight vector parameter of the model. So you can think of a linear model as the unnormalized sign distance, right? So this is the positive distance, this is a negative distance, and so on and so forth. And this is not really relevant to the class, but this is how you can interpret how the bias affects the shift of the hyperplane. Okay, so how do we maximize the margin, right? So intuitively, it makes sense that we want to find the W or the H in this case. That is the hyperplane that creates the maximum separability between the positive and negative points, as measured by this distance between the closest positive point and the closest negative point to this hyperplane. The way we can optimize for that is, well, we can write down the formula, right? Recall that this distance is this, right? This is the sign distance. And so just to back up a little bit. So this is the sign distance. So it's positive for points on this side of the hyperplane. It's negative for points on this side of the hyperplane. The label is either +1 or -1, right? So the sign distance multiplied by the label should always be positive, or we have 100% accuracy on the training set, right? Because if this sign distance is negative for a negative data point, the y is negative. And if the sign distance is positive for a positive data point, the y is positive. So of the hyperplanes that always achieve positive sign distance times the label, what is the one that maximizes the margin? Well, the margin is simply the minimizer over this quantity, right? This is the sign distance times the label of every data point in our training set. The one that has the minimum such distance is the one that defines the margin, right? These 2 points are the ones that have the minimum such distance. So the optimization problem, we can phrase it simply as finding the parameters W and B that maximizes the minimum distance. And that's when the margin is the minimum distance. Any questions on that? Yeah?
So this will still work if the points are not linearly separable?
Not as stated. For the next 2 or 3 slides, let's pretend it's linearly separable, then I'll show you relaxation. Okay. So how do we solve this problem? So this problem is, this problem as stated is hard to solve, right? Because we're dividing by the W that's part of my optimization parameters. So this is not necessarily the form of the problem that I would like to solve. There are other equivalent forms, which I'll show you in this slide. So here's a different formulation. Suppose this is basically just whatever this score is, I'm just dividing by the norm of W, right? So it's equivalent to just say, I want to find all W and B, constrained to the norm of W being 1, minimizing this. Maximizing this quantity, excuse me. These two will give you this exact same solution in terms of accuracy. These two will find the exact same hyperplane, perhaps modulo scale. Right. For this one, if you scale the W by 100, you divide by, so this score is 100 bigger, and you divide by 100, it all gets divided like that. For this one, you just say the norm of W has to be 1. I'm just going to find the hyperplane that, with one norm that maximizes the margin. Okay, but this is still, in some sense, a little bit hard to optimize because it's like a max over a min, right? Here's another formulation that's much easier to reason about mathematically. Suppose we enforce instead not that the norm of the W was 1, but that but that the minimum margin, that the margin is 1. Right? I'm supposed to enforce that instead. Then it turns out that finding this hyperplane is equivalent with this constraint is equivalent to this, right? I want to find a W with minimum. I want to find a W with minimum inverse norm. Okay, I'm sorry. It's not inverse norm. It's just sorry. It's not supposed to be 1 over the norm. I'll change that. That's a typo. It's just the norm. And the way you can think about this is that this is supposed to be 1, and this is a maximization problem. So if you want to turn this into a minimization problem, all you got to do is invert this, right? This is guaranteed to be 1. We enforce it to be 1, and we want to turn this maximization problem into a minimization problem. So we just flip the denominator and numerator. This is 1, so it doesn't matter, and so it actually just looks like this. Sorry about this. I'll change this in a second after class. So this is the formulation of a support vector machine. So these are the positive points. These are negative points. This is the point where W transpose X minus B is equal to 1, and this is where it equals minus 1. Right here. The margin is exactly 2 over the normal of W. And it's equivalent, and you could solve this by simply finding the minimization of this problem. So minimizing the squared norm of the W vector such that for all training examples, the sign distance, the unnormalized sign distance of this training example times the label is at least 1. Any questions? Sorry, yeah?
Sorry, it's not clear to me how why we can set the minimum distance to be 1 or the numerator.
Okay, you can set it to any constant you want, and then this would just be scaled by a constant. But the scaling of a constant does not change. So this is not the minimum, this is the argument, which means I just want to find the W I just want the parameter that minimizes it. So if I set this to like 3, I can scale everything up and it'll give you the exact same answer. A modulo scale. So the choice of 1 is in some sense arbitrary, but everything's invariant to scaling. So in this way, a support vector machine is called a maximum margin classifier, and in particular, these are known as the support vectors, these 3 points. These are the 3 points that lie on the margin, right? In an SVM, because of the way it's formulated, there will always exist, for binary classification, at least 2 points that lie on the margin, one on the positive side, one on the negative side. And they are called the support vectors. And in some sense, here's how you can think about this having good generalization error, right? Good generalization performance. If I were to resample this training set, right, and get a slightly different answer, and some of these data points get jiggled a little bit, but some of them stay the same, I will get the exact same solution as long as these 3 points stay the same, right? If I subsample this, let's think of a different thought experiment. If I subsample my training set so that I don't train on everything, so long as my subsample includes these 3 examples, this optimization problem returns the exact same solution. It's robust in that sense. Right? And if you're interested in this analysis, there's a link here with the analysis, more formally stated. So in some sense, only the training data that lie on the margin matter. All the other training data are irrelevant. Now you might be wondering, this does not look like the kind of loss functions that we've been talking about in class, right? How does this relate to the loss function formulation that we've been talking about in class? This is, and so I'll show you that connection in just the next slide. This is just a geometric interpretation. And this only applies for linearly separable models. And as Ellen was asking, what happens if the training problem is not linearly separable? And that's called a soft margin support vector machine, right? Suppose that we have these examples. And so these 2 examples make them off. The introduction of these 2 training examples makes the problem not linearly separable. Right? And so what happens now is that we still solve the exact same optimization problem, but we introduce what's known as a slack variable. And in this particular formulation, we have one slack variable per training example. And how this works is that we want every training example to be classified beyond the margin minus a slack. So what that means is we want to minimize this trade-off between the size of the margin. The larger the margin, the more stable our model is, and the size of the margin violations, how much error we're tolerating in terms of margin violation. So in this particular case, we suffer a slack margin violation of this distance plus this distance. So this is how you handle the case when the training set is not linearly separable, which is by and large all the time in real world problems. So just an aside, the notion of these kind of slack variables is very prevalent in many optimization methods. This is just one. This is just one that tends to have nice geometric and statistical robustness guarantees as well. So okay, so now we take a look at this and we say, okay, can we rewrite this in the form of a loss function, like the ones we've seen in class? And the answer is yes. It's called the Hinge loss. So an SVM, also known as a max margin, a support vector is also known as a max margin classifier. That's where the training examples are that lie on the margin known as support vectors, is equivalent to so finding such a classifier with these support vectors is equivalent to finding a model that minimizes the hinge loss, right? So this term is called a regularization term, which you can just ignore for now. We'll talk about regularization in greater depth in the next lecture. You could you can just think of regularization as a way of controlling for model complexity, right? So in some sense, you know, the bigger the margin, the more stable the model is. So in some sense, the more simple the model is. We'll talk about it in more greater depth in the next lecture. But now let's focus on this term, right? This term can be rewritten, like these slack variables can be rewritten as this, which I can define as the loss function. So let's think about how this works, right? We want to guarantee, we want this slack variable set such that all of these inequalities are satisfied. What does that mean? That means if, for example I, the score that we predict for this example is less than 1, then the slack variable needs to be greater than 0 in order for this inequality to be satisfied, right? So when the score times the target, in which case the target is positive, when the score is greater than 1, then this equality is naturally satisfied without the slack variable being required, so the slack variable is 0, so the loss is 0. As this score is less than 1, becomes less than 1, in order for this inequality to be satisfied, the slack variable has to be greater than 0. And the amount to which it needs to be greater than 0 is exactly the amount at which it needs for this thing to equal 1. So if the score is 0.5 and the slack variable is 0.5, right? And so that's exactly known as, defined by this formula, which is called the hinge loss. It's called the hinge loss because there's a single hinge right here. It's kind of a lame name, maybe, but so that's why it's called the hinge loss. And it actually is it's a surrogate for 0, 1 loss. It is a convex upper bound on 0, 1 loss, so it is relatively easy to optimize for the hinge loss at training time. Any questions on that? Okay, so let's think about hinge loss versus squared loss. Oops. Let's think about hinge loss versus squared loss. So squared loss looks like this, hinge loss looks like this. So can anyone sort of notice any nice properties of hinge loss compared to squared loss if our goal is to minimize 0, 1 loss? If our goal is to minimize 0, 1 loss, and we can't actually minimize it directly because it's flat or discontinuous everywhere, and we have to pick a surrogate loss function to minimize, what are some advantages of choosing hinge loss over square loss? Yeah?
Except in like the small region between 0 and 1.
I'm sorry, I didn't hear that.
Except in the small region between like 0 and 1, it's like a tighter bound.
It isn't, yes, that's right. So the fact that it's a quadratic curve Like even if you rescale things, because it's a quadratic curve, yes, it's not robust to outlier predictions. But there's also another reason. Yep.
It's not symmetric like the square loss is.
Right. So square loss is commonly that's right. So square loss is commonly used to minimize regression error, where the goal is to predict a specific real value, right? In classification, the goal is to say for the positive examples, the sign of the function needs to be positive. For negative examples, the sign of the function needs to be negative. So if I'm more positive than before, I shouldn't get penalized for that, right? Like this model will say, I'm penalized for being overly confident that this example is positive. That doesn't make much sense. Of course, if you get perfect square loss, you get perfect zone 1 loss. But if you get imperfect square loss, and most problems you cannot learn the training set perfectly unless you're overfitting to it, then the trade-offs your model is making is saying something like, if I predict this example as negative 0.5, I incur the same loss as if I predicted it as 2.5. And that doesn't make any sense if the label is 1. Right? So when you're making trade-offs, because it's impossible, because you don't want to overfit the data, so you're learning a model that has trade-offs in loss, it doesn't make any sense to make that a penalty because you're not doing regression, you're doing classification. And hinge loss is asymmetric. If you're beyond the margin for positive examples, then you don't incur any loss whatsoever. So in the previous lecture, we also talked about what loss function the perceptron is implicitly optimizing in its algorithm, in the perceptron learning algorithm. And that, recall that it looked like this, and the loss function looked like this. And it's actually very similar to the hinge loss. The only difference is that the hinge loss requires a margin, right? You have to be confident. You have to be confident of the correct prediction to beyond a certain margin. Otherwise you incur a loss. Whereas the perceptron does not enforce that. And this is part of the reason why the perceptron can converge to any model that's in the linearly separable regime, whereas the SVM converges to the maximum margin model. Any questions? Okay. So just to summarize support vector machines, we've seen this objective function. This is the objective function that support vector machine is optimized. If you try a support vector machine in scikit-learn, it's solving this equation. I should mention that C here is a tuning parameter, which we'll talk about in greater depth in the next lecture, which trades off between complexity and loss, right? If C is really large, then I want to find a W that minimizes the margin. I want to find a W that has no margin violations at all. The actual margin might be very small. If C is 0, then I could have I don't care about loss at all. So the first interpretation is geometric. It's a trade-off between the size of the margin and the amount of margin violations. The second interpretation is that we're doing standard loss minimization, as we been talking about for lectures now. And that's a measure of model complexity, as measured by the two-norm parameter vector, versus the hinge loss. And again, these two interpretations are equivalent. Just a comment on optimization. So, this function is not smooth, right? This hinge loss parameter, looks like the max function, is not smooth. So it's not differentiable, at least at the hinge point. So how do you optimize for this? Turns out the SPD actually works just fine if you're into that kind of thing, which I am. And instead of doing gradient descent, there's a notion of that there's a generalization of gradient descent called subgradient descent. And as long as you use the subgradient descent, the whole thing works just fine. There are more sophisticated methods, and we'll talk about that in a future recitation that you can use that can train this in a more stable, faster convergence kind of way. And that's more applicable in general to non-smooth, convex optimization. It's called iterative thresholding. And we'll talk about that in a future recitation. It's for the most part beyond the scope of this course, although you may find it useful for some of the mini projects if you want to use those types of methods. But just subgradient descent works. Subgradient is a generalization of gradient, that exists for all convex that you can sort of use for all convex optimization problems, including those that are not always differentiable, such as linear. Any questions on SVMs before we jump topics? Yeah.
So does scikit-learn use this, or do you specify each time the method that's actually going to solve an SVM?
It's a great question. I don't actually know what they use. I mean, I don't know. I mean, certainly for large data sets, like really large data sets, they use mini-batch stochastic subgradient descent. There's nothing else. It's hard to scale that to anything else. For intermediate sized data sets, you could use other things too. I should mention that, okay, I see your question. Okay, let me rephrase it, because what I said was not entirely correct. You can do iterative thresholding in a mini-batch setting. Just come to recitation in a few weeks, and I'll explain this in more detail. I'll explain in more detail. I don't know exactly what scikit-learn is. Okay, so now let's move on to logistic regression, also known, perhaps incorrectly, as log linear models. So this is what logistic regression looks like. It's actually a probabilistic model. It posits that there's a probability. Again, this is just for binary classification of y of the label y being being 1 or -1 for some input x. And it's a standard S-shaped curve, and this S-shaped curve is defined by this formula. You could rearrange terms, and it looks like this. And this is known as a log linear model. If you take the log of it, it looks kind of linear. And it's linear in the exponent, so if you take the log of the exponent, it's linear. That's the the way the reasoning goes. And so if you can plot this for yourself in MATLAB or Python, this type of curve, as you increase the scoring function, probability that y equals this label y equals to 1, and then as this drops to negative, it goes to 0. And by the way, this function, you can equivalently write it like this, or like this, or like this. It's called a sigmoid function. So the way you think about training a logistic regression model is, well, you're also minimizing a loss function, but the way you sort of derive it, you can derive it using more from a probabilistic principle. And the idea is as follows. Suppose we have a training set of the following form, the standard training set. And suppose that every example in this training set was sampled independently from the test distribution, the true distribution. Then we want to find a model of this form that maximizes the likelihood of the probability that our model predicts the correct label given this input. And because every training point is independent, that is equal to decomposing into the product of each training example. And, I gave the answer. Oh, okay, well, anyways. And it's because each has, okay. When I went through this slide last night, it was backwards how I'm presenting it right now. But anyways, now you have the answer. So because each training example is sampled independently, we can decompose the likelihood into a product. And if you're unfamiliar with this type of decomposition because of independence, we'll cover probability in recitation next Thursday. Okay, so why would we use logistic regression, right? It is the case that SVMs are often better at classification, especially if there is a notion of margin, right? If things are approximately linearly separable with a few sort of violating examples, SVMs are often better, much better, and faster to optimize than logistic regression. The reason why you want to use logistic regression is because sometimes there's just inherent uncertainty in the data set, right? Sometimes for a certain type of input type, it really is 80% positive and 20% negative. You can't do better than that. It's just inherently uncertain. Okay. And in those cases, what you want is you want to predict calibrated probabilities. Right? If the weather forecast predicts an 80% chance of rain, for the similar type of scenario, it should rain 8 out of 10 times that it makes such a prediction. Right? So one question is, for an SVM, it doesn't predict the probability; it just predicts some real value that's maximizing margin, right? So one can actually use one can actually measure this effect, right? So this is f of x. So this is the scoring rule. This is the scoring rule of in this case, a model of decision trees, although SVMs have the same effect. And as you increase the scoring rule, increase the score of the scoring rule of this model that's not a logistic regression, this is the actual probability of the label being +1, right? If the probabilities are actually calibrated, then they should lie on this line, right? If the scoring rule predicts this number, it should be 20%, this number, so on and so forth. It should lie on a linear line if this is predicting something that corresponds to a calibrated probability. But as we can see, it is not predicting something that lies in this line. And I should mention how this data was generated was the scoring function. We took a train model, we took the examples, we scored all of them, and then we bucket them into discrete buckets, and then we measured the fraction of examples in each of these buckets that has a positive label. So that's how these points were plotted. And if the scoring rule corresponded to any notion of calibrated probabilities, these plots from these buckets should lie on a linear slope, which it does not. So this is a well-known problem that SVMs have, and other models too, which we'll talk about later in the course. So, well, what does this look like? It looks like an S-shaped curve, right? It turns out that we can actually take the output of an SVM and fit a one-dimensional logistic regression model on it, where the input feature to the logistic regression is the score of the SVM, and then you can actually recalibrate the score of the SVM into probabilities. This method is known as plot scaling. If you want more details, it's in this paper. And of course, we could also just train a logistic regression on the actual raw features and not on the output of an SVM. That also works. Okay, so what is the loss function? Oh, by the way, does anyone have any questions on this slide? Yeah.
Can you explain the last part again? This you said on top of the...
Right. So imagine a logistic regression model that takes as input a single feature, a one-dimensional feature, right? What is that feature? That feature is the score of an SVM or some other model that's not calibrated, right? Empirically, what people find is that for models like SVMs and decision trees, which we'll talk about later in the course, when they predict a score, as the score increases, the probability of the positive label, let's say, increases superlinearly and then sublinearly, right? And if you look at this type of function, right, it's basically saying, pretend that x is the score of pretend that there's a single x, one-dimensional x, and it's the output of an SVM. We want to convert the output of an SVM into a calibrated probability, right? Like when SVM predicts this score, it corresponds to 80% chance that the label